चीज अपना ही है।
हेलो हेलो।
Hello. There is no sound from the other side. Hello. Yes. Hello. Hello. Yes. Hello. Am I audible? ये कैसे है? Not writing. ये लिख नहीं रहा actually. ये लिख नहीं रहा.
इसको मिनिमाइज किया ना इसको ऊपर एक्चुअली चले ओके
Hello. Okay. So full screen कैसे? हाँ? So good afternoon, everyone. So my talk is on the study of beam resonances in MEHPA 1. So in any high intensity accelerator, if you see, so which are now being proposed for various applications, they all require to operate at very high beam currents. And at these high currents, the nonlinear space charge forces are very high, and these can lead to increase in beam emittance and the formation of beam halos. So the main design goal in any high intensity accelerator is to allow hands-on maintenance. So as to allow hands-on maintenance is to minimize the beam loss by avoiding or minimizing any contributions of various halo forming mechanisms. Now what is beam halo? They are, if you see the beam, they are a small fraction of particles that are away from the beam core. So these particles, they go far away from the beam core, and they can get lost in the accelerator, and thereby causing they can activate the structure of the accelerator and limiting hands-on maintenance of the structure. So there are several beam loss mechanisms which can cause these beam halos, resulting in beam loss. Out of these, what we are going to, what we have studied here is the coherent and incoherent resonance effects arising from the nonlinear space charge forces exerted by a high intensity beam. So here coherent forces, coherent effects, they originate from the collective dynamics of the beam. That means the beam as a whole goes into resonance, or some sort of instability is excited. Whereas incoherent effects, these refer to the behavior of individual particles, so single particles within the beam. So this happens because all lattices, focusing lattices in the accelerator, these are periodic. So periodically the beam is focused using periodically arranged magnets. So because of this, the resonances arise. So for example, let's say, let's consider a drift tube Linac. So in the drift tube Linac, we have various drift tubes, and quadrupoles are used for focusing the beam. So if you see inside the drift tubes, there are quadrupole magnets. These are used for focusing the beams, and these are arranged in a periodic manner. So for example, it could be, there could be a focusing magnet here followed by a defocusing magnet, again a focusing, defocusing, or a FFDD type of structure, or so whatever it is, it will be a periodically focusing structure. Even if you go to a single spoke resonator, so here also in between the spoke resonators, solenoids are used for focusing the beam, which are again arranged in a periodic manner. So due to these periodic arrangements, the resonances come into picture. So I'll explain these resonances before going to the resonances in MEPA1. So for that, we define the zero current phase advance, which is given by this expression here. So here K represents the focusing of the quadrupole or the solenoid magnets. And so this zero current phase advance, it tells us about the strength of the external focusing. So whether it is the quadrupole magnets or the solenoids, it tells us about the strength of the external focusing in the periodic focusing lattice. Now when the beam comes into picture, so since the beam the beam has some current, and there is space charge which causes defocusing in the beam. So there is the net effect of that is taken care of by the for that we define the full current phase advance, which is given by this expression here for x and y, where the epsilon denotes the emittance, and x and y represent the beam envelope in x and y. So coming to the coherent effects first, the coherent effects, these are the collective effects of the beam as a whole. So that means the envelope, the beam envelope as a whole. So let's say for a well-designed any ideal accelerator, there exists a unique set of initial conditions. So that means this is the beam envelope in a, let's say in an accelerator. And you can see that at the end of one period, this repeats. So that means the beam size and the beam divergence at the end of one period is the same. So both in x and in y. So here 0 denotes the x and y for the matched case. Now, if a beam that is matched at the entrance of the Linac, it remains matched throughout the Linac. And if you see the Poincare of this in phase space, then you can see that the matched beam is represented by a stable fixed point in the phase space. So for example, this is repeating after one period. Whereas if there is a beam mismatch, so we see that now there are, so the beam is not periodic, the oscillations are not periodic, they are sort of quasi-periodic. So if you see the Poincare of the mismatched beam here, so it is seen as orbits around the matched beam. So these, depending on the level of mismatch, these orbits represent the mismatched beam in the Poincare map. Due to mismatch, it can also give rise to envelope resonances. So again, if you see this Poincare, this is the fourth order. This is the fourth order envelope resonance. So the envelope, if you see, it is if you see the Poincare of the envelope, it is there are four islands being formed here in the RR prime phase space. Similarly, there is a fifth order resonance, and so on. So several resonances will be formed due to the mismatch. And if the beam current is very high, then we can see that the phase space here, the RR prime, this becomes very chaotic, and this can lead to chaos. So the envelope resonances, these are a coherent effect of the beam envelope, and they are excited in the presence of the beam mismatch. So these are basically resonances of the envelope as a whole. The beam mismatch can cause increase in beam size, and it can lead to envelope resonances and also chaotic orbits when the space charge forces is high. So you have to avoid these, otherwise this will lead to increase in beam size, beam emittance, also halo formation, and the beam will get lost. In the coherent effects, the second order envelope instability is widely studied. So because the second order envelope resonance, this is actually an instability. So it is a collective effect arising from the interactions between the focusing structure and the envelope oscillation mode. This is excited for sigma 0 greater than 90 for a range of sigma values. So you can see here, this is sigma 0 and this is sigma. So for a periodic lattice, when the phase advance, so the zero current phase advance exceeds 90, then for a range of sigma values, the envelope instability is excited. So the second order envelope instability is a collective behavior of the entire beam, and it is marked by irregular changes in the beam envelope. If you see the beam envelope, now there are irregular changes in the beam envelope. So this is triggered by a mismatch, and it is also characterized by the non-existence of the fixed point in the Poincare phase space plot. So if you see the envelope Poincare for the envelope in phase space, you see that there is no fixed point, and in fact it is forming an S type structure. So the beam evolves into a two-fold structure in phase space. So if you see the beam as a whole, due to the envelope instability in phase space, it will evolve into a S-shaped structure, which is like this. So this is an effect, this is an instability which is to be avoided, otherwise it leads to large increase in emittance. Now let's see the incoherent effects. So these are basically single particle effects. So these arise from the interaction between individual particles. So unlike coherent effects where it was excited by the envelope as a whole, here only a few individual particles are participating in the resonance. So this is from the interaction between individual particles and the focusing forces within the accelerator lattice. These are referred to as incoherent resonances of individual particles. Now, any nth order single particle resonance, it is an incoherent effect that is excited when the resonance condition nkxy is equal to 360 degrees satisfied, where here this kxy is the phase advance per focusing period of a single particle in the x or y direction, and n is the order of the resonance. So this is excited by the nonlinear term of the space charge in the Hamiltonian of the equation of motion. So here, this is mainly due to the nonlinear term. The more nonlinear the beam, the higher is the incoherent effect that is seen. So as an example of the incoherent effect, let's say the fourth order resonance. So here n is equal to 4. In that case, the fourth order single particle resonance is excited. So here you can see in phase space, you can see a four-fold structure is formed in phase space. So this is typical of the fourth order resonance. You can also see there are just a few particles that are going far away from the core of the beam, and so not the entire beam doesn't participate in the resonance. Just there are few particles that are participating in the resonance, and they contribute to the increase in beam size or the beam halo. So these particles, so the particles that are in resonance, they take 4 envelope periods to complete one period. So if you see, this is the blue line here. The blue envelope denotes the envelope, and the red one is the particle. So for one oscillation of the particle, it takes place in 4 envelope oscillations. So in this case, the particles that lie on the resonance, they have a tune value of 0.25. So you can do a FFT, and you can get, so the tune of these particles comes out to be 0.25, where tune is defined as the number of oscillations in the horizontal or vertical plane per period of the lattice. So these are the coherent and incoherent effects. Now, the dominant of these effects are the second order envelope instability, which is a coherent effect, and the fourth order resonance, which is a incoherent effect or a single particle resonance. Both of these are excited for sigma 0 greater than 90 degrees. So when sigma 0 is greater than 90, the conditions for both of these are satisfied. So in this case, it is seen that, so here we can see that in this case, both the conditions for both are satisfied. In this case, the fourth order resonance is excited first. So if you see the beam envelope here, so it is gradually increasing, and you can see here initially, if you see the phase space, it is a four-fold structure. Later on, after some time, as the mismatch grows, because the second order instability will come only after the mismatch, we see that this four-fold structure evolves into a sort of S-shaped structure or a two-fold structure. So once the envelope instability, so then the envelope instability gets excited. So once it is excited, it dominates over the fourth order resonance. And we see that the four-fold structure evolves into two-fold or S-shaped structure in phase space. Okay. When either of the effects is excited and the beam evolves self-consistently, you can see that the beam emittance as well as the phase advance increases and the beam tries to comes out of it. So when the beam phase advance crosses 90 degree, the conditions for neither of them are satisfied, and then in that case the beam will evolve into a new equilibrium. So here you can see that it is again becoming like a normal beam, and there is no trace of either the fourth order resonance or the envelope instability. So we've studied these effects in MEPA, mainly in the MEPA DTL and SSRB. DTL accelerates the beam from 3 MeV to 10 MeV and to 40 MeV using the SSRB cavities. So the variation of RMS normalized emittance as a function of zero current phase advance for a beam current of 10 milliamperes has been seen. And this is done for both FFDD for Gaussian and for uniform. And we see that there is a increase in emittance beyond 90 degree, and for the Gaussian beam there is an increase in emittance at around 120 degree as well. So we've analyzed this. So around 90 degrees. So let's say at 95.5 degree. So we see that here, if we see that the emittance is increasing here. And if you see the phase space, we see only the traces of only the fourth order resonance. No envelope instability is seen. And if you see the tune of these particles, this also comes out to be 0.25. The envelope instability is not seen. So this is because the LIPA DTL is a short structure, and only the fourth order resonance gets excited. There is no time for the envelope instability to get excited. If it was a longer structure, after some time, the envelope instability would have got excited, but here only the fourth order resonance is excited. For sigma 0 is equal to 125, we see that a six-fold structure is seen. But if you see that, it takes the selected particles. If you choose particles on the resonance, it takes the selected particles 3 periods to come back to the same position in phase space, indicating that this is a third order resonance. And here, if you see the tune of the particles, it is 1 by 3.347 for a.
Rajni, please try to wind up in 1 minute.
Yes, sir. So it is the third order resonance. We've also seen studied for the MEPA SSR, and here we see only, we see an increase in emittance in this region beyond the 90 degree, and here it is only due to the fourth order resonance. Also, if you see, the fourth order resonance is not as pronounced as in the case of DTL. So here, and also the third order resonance is not seen. So just summarizing now, we have done the studies for both SSR and DTL in MEPA 1. And we see that for both the cases, for sigma 0 greater than 90, there is an increase in emittance. And for both the cases, it is seen that the envelope instability is not excited. It is only due to the fourth order resonance. We also see an increase in emittance in the DTL at around 120 degree. For the Gaussian beam, not for the uniform beam, and this is due to the third order resonance. The increase in emittance in the SSR is less than in the DTL. So the fourth order resonance is less as compared to that in the DTL. So based on these studies, MEPA 1 Linac will be operated in at safe values of the sigma 0 to avoid these resonances and instability. Thank you.
Yeah, thank you, Rajni, for a nice presentation. Since we are running late and somehow the audio here is not working, we will not be able to take up the questions. But thanks a lot. And we wanted to present a memento. Since you are not here, that will reach you. Okay. Thank you.
Thank you, sir.
Bye.
We discussed redesign for the booster synchrotron industry. We are planning to build industry 4 generation synchronization flows. For industry, the booster will serve as an injector. So all we want to inject the beam industry in the top of mode. During the beam injection, we are using the pulse system and pulse multiple magnet, non-linear magnet. And so our goal is that we should minimize the oscillation during beam injection because we are using only we are not using the whole kicker because we are using industry 2. So the main challenge that the injected beam from the booster should be as small as possible so that we can transfer down of the injection industry. So we will design the booster in such a way that its impedance should be kept minimum. This is our main goal, and we want to get the beam 500 mm beam from the Linac. The beam of the beam is very hard. Its spread is 0.5%, release stability is 0.5%. To accommodate the Linac beam, we have to design the dynamic aperture. The beam in such a way, and another problem is that we are using the long circumference. For booster circumference around 900 meters. It is coincidence with the ring circumference, very long circumference. So it will use the impedance problem. So it will use the we cannot get inject the beam. Suppose we inject the beam, the instability problem is very severe. So our optics we will design the optics in a such a way that this optics should be less, so that we can easily commission the beam. And another challenge is that there are the power converter will vary from 100 to 6 dB. So dynamic range is 1 times higher. So there is some cracking error. So all the power supply, all the system should not follow in the same way. So there is also error. So we can also accommodate this error in the design. So our main goal is that we should design the system in such a way that we can accommodate all the error. So that is our basic goal. So normally in the literature, you can find that the polarity and modified code. People are using both that is photorealistic and modified code. But we are using we have just studied from the modified code development. Normally there is no nobody has the development studies or these are just opposite, but they are not effective because now they are taking time of the year. So we will give the criteria. We are using the DBA, what is the why we are DBA is better than the model. So during the presentation, we'll discuss the difference of photorealistic modified to DBH and we are for the DBH will use the presentation of this topic. So this is for strategy production. modified probability, two candidate values. We will compare both values and decay on the basis of injection energy, that is stability, linear analysis, tapping, and linear efficiency, and other statistics and the So this is the booster. We can see that the booster and the ring both share the same line, and we increase the conductivity from the booster conductivity the ring the 60 and we then shifted from the booster and the ring. So for transparent down injection, here is the complex deep injection with down a finger, and so that we wanted to be using of the booster to be less than 10 otherwise our injection is go down in the industry, and so this is our main requirement. So though it is difficult, it is separate matter also because the DVR is a low K material. So the addition is the user on the board, the prospect of the user and on the date of the material. This is also required to be from the business to be as the best possible. So this is the question criteria. We are using the location of the physical surface, not the swimming surface. It's 900 meters, and this is the free water and the lakes and to get higher surface. Because the injection is we are getting the we have the relief from the community, 41 meters, energy strength 0.5 and efficiency is 0.1. And during mapping, there are so many errors, of method control, and there are other so during this period, we want to control below. That is the main objective. And we want to if you take any problem, so our objects will be available. So we can raise objects and we can accommodate the and get so for proper conditions to be during the commissioning, so we are high impedance because our room is very large, so the impedance is very large. So we can get these unit only the solar there is 2.5 millimeter. So very small. Compensate the effect of the high impedance. We put the operate the machine very high percent of the system. We save the commissioning of plus 4. So the high lifespan of the particle, the system of the knowledge velocity. So the machine direct will be reduced and we not protect it. So further for downstream section, we get high beta function, small beta function, or injection, extraction, and cavities. So this is the normally this is the impedance. Impedance bound by the bending angle. We can use the bending angle. It can be reduced. Further, we can take the help of the lattice. This is called the lattice structure C. If we put many small bending angle, the dispersion function will be very small. So higher span of 64 minutes is required. So the machine will become more non-linear. So we have kept the bending magnet 88, and now we play the lattice constant C. So these are the lattice constant. So this is the minimum impedance we can operate. So here we think we cannot adopt the modulation structure because the photo we are getting 23 number, but we can use double band, multi-band. So our impedance can go down. So normally people are using modified modalities all over the world, but we are getting some difficulties. So we are also studying the development. So this is the modified probabilities. It is very simple structure. We have kept bending magnet as 2D component. One is the fixing component, the bending magnet, and one is the part of fixing component. So this is itself of the two magnet, bending magnet and here. So here further we put higher between bending magnet and here, so that we can get we can reduce the strength of the sustainable magnet by increasing the dispersion function and beta function and better decoupling the beta function. So we have kept down this with function particle and bending magnet. And these get also used for beam injection RRCAT. And further we want to this the probability. So we have done study by measuring the length of the bending. If we increase the bending magnet, so our natural probability will be it is not that system is opposite. So beneficial for us to go with the higher And the number less related was less compared to the other in the particular. It is a systematic step will be further. And this number days of the ventilator also reduce the RFR requirement from the RF requirement. So this is the modified quality. So we have to calculate a technique itself, and you can see the laser produce is very small, minus 38, minus 27, and we can get the 430. And but however, we are getting low voltage picture because we are indicating the beam here. So here beta function is small at the injection point, and dispersion function is very high. So during the overcome this, we are doing on axis beam injection, and for fixation of the QD component, so how we can put the QD component in the band divider. So we want to get out the system of great so we have to expect one at this response. So based on this, we have kept the QD component in the fixed in the band divider. But still there the defoxing formula there is the band divider, and we are not getting good decoupling between the body and beta function, and this is a very large of the system of matrix required. So now we want to see for the development experiment. So we are not operating development experiment as the experiment because we are operating the development experiment as the condition. Their index condition based on is very large, is very large. So we are operating development experiment as a non-experimental condition, and we have operated for the long low level phase bar. We are getting the low level phase bar. We operate the DPA in the non-experimental condition. So for this condition, we have to find out the QB here, QB, forward decoxing, bending away, forward decoxing, forward foxing, forward decoxing, forward decoxing. This combination will give the low phase bar. So we have created this combination, and we have get the long fixed meter for the beam injection, and in the experiment, we have optimized the weight, the 20 here in such a way that we can get low test resistance. So you can see that if you affect the benefit to be small, then the resistance is very high. That's my. But we increase the gap, then our resistance will be reduced drastically. So we have optimized the gap, decide the gap here in such a way that we get higher octane solution as well as we get low system resistance. This is the optimized DPA structure. So here we have multiple structure, but here you can see here we have kept very high but here the resistance is very high as compared to the Kubernetes. And we can also reduce the beam 500. So this current hard change. As a will not change. So this is almost again the same. So now that is the advantage that we are saying here the gate between injection cycle time is 1 and 2 meters. Now it is only 4 meters. So this gate will reduce the peaker strength as a result of that undershoot of the peaker pump after the when the peaker switch off will be reduced, and we can also polypart of the injection get less than 1 microsecond. And we can also for injection because here we can reduce the injection by almost half by increasing rate. So the injection reduce the injection the sensitivity towards injected beam potential will also be reduced. And here you can see the diameter of the model. Here is very small diameter plus minus 5 mm, but in the DV structure we have very almost plus minus 2 mm. And the vertical approach is also very high. In the movement time acceptance for component is very high. Here it is small. So from this point of view, the DPA rate is better as compared to the modified rate. Further, you see that in the process of the direct injection, the DPA is small in the process of material, but in the Kubernetes, the DPA is very high. And here we see the effect of the here the evolution factor aligned with in the portable manner. This is the evolution factor is given by, and this evolution factor depends on the summation over the portable. So in the DV here using 4 portable. So definitely the evolution factor plus those are beta wave is higher in the DV rate as compared to the portable rate. So these are the similar results. In the global evolution factor is only you can see that factor is increased by 15%, 15% the DV rate as compared to the portable rate. And we also done similar result that we still have 1,000 plus by 30. It is tolerable plus 35 in the possibility, but it produces 25 plus 25 the degree. And since in the that is the high plasma is required, so the number of degree is large and in the degree is 20, but here it is only 1. Now we have the additional capability in the we cannot fill the body part because we have a two component ventilator to be here. So we have put additional theory component and based on this we have done the realistic. You can see this is the vertical capability, there is the ultimate. But we cannot reduce the system strength by a large amount. The system strength reduction is only 30%. And the twist parameter will be have asymmetric variation. As a result, the testing of variance will be increased comparable to the daily rate. So we will not get any advantage of the modified condition. Now you can see that DB lattice, we can vary, you can see this limited. We can vary increase from 2 nanometer rate to 50 nanometer. And we can also reduce the distance from 10 to almost from 30 to very small, 5, 6. So we can place the objects in a body. And this is the ramping here because this is the energy ramping. The all converter has some error. They have some accuracy. It cannot follow closely because the memory design that we can go up to 200 million. In the modified quality, the twin spread, which is very small, is small as compared to the degrade. Degrade is higher, but in modified quality is small. In this point of view, is better. Here you are also not taking additional polymer component. If you take additional polymer component, then this will also replace and maybe go to the comparator degrade. So from this point of view, it is also degrade whatever. Not the degrade. This is modified one by mistake. And so you have to okay. Just from the section you can see that we have 3 bumper magnet and we have the very basic step of the beam inspection and the beam extended beam is passed over the sustainable magnet. So this is very sensitive. But in the case of the deviation, we have long section and we can put 4 bumper magnets. We can generate the cross beam and the beam extended beam is not possible with any sustainable magnet. Further, we get the beam at high intensity. We can also build this beam at the 6 dB and so we have the benefit. Further, we can reduce the injected beam oscillation because there the dispersion would be small. So we can put the efficient circumference near to the design orbit. So we can reduce the spread of the buffer magnet and gigabit. So this is the conclusion. The modified lattice are different change this parameter, but but in DB lattice we can get large amount of aperture and driving acceptance. In modified lattice, the range is not sufficient, but in the DB lattice it is sufficient as it is available. And the period of injection oscillation will not be there. So the tracking will be very serious, and we have seen that the tracking is 0.05. So the large part of the beam will be dropped, and the injected beam will be dropped. And they will be. Thank you.
Thank you for Sir, thank you. इसको
So Riyasat, sorry for the interruption.
PPT
अभी start करते हैं.
PPT चला सर. Hello. So, thank you for the organizers of InPAC giving this opportunity to talk about the progress on the lattice design, studies of the storage ring of industry, which is well thought of high Abelian synchrotron addition source in India. So, चित्रा जी नहीं चलना है चलो. So outline of this presentation is I will give you the design goal of this facility and this facility layout, and ultimate goal of this fourth generation light source to have a lower brilliance, the lower beam emittance to enhance the photon beam brightness. So there are conventional mean of minimizing the beam emittance based on the homogeneous field dipole and including the combined function dipole magnet. So this is the you can say the workhorse for the third generation light sources in general. And for the fourth generation light sources, there are the conventional means of having different profiles in the dipole magnets. The one is the longitudinal gradient band and also including the anti-banding in the focusing quadrupole magnets. So based on this, I will talk about the lattice version 2 and give you some details on the linear lattice and the nonlinear lattice performance. And further, we are improving this lattice version 2, and I will highlight some recent consideration which is converging towards the lattice version 2.1. And finally, I will summarize this talk. So as far as the design goal is concerned, so we have the requirement of generating the photons with peak brilliance of 10 to the power 22 in standard units, and the maximum photon energy which should be available is up to 200 keV from advanced insertion devices. So more on this parameters and the science will be a talk by Dr. Tapas Ganguly on March 28. And when we translate these requirements into the electron beam parameters, so we need an electron storage ring of 6 GeV, and the beam emittance has to be better than or equal to 150 picometer rad, and the beam current is 200 milliampere, and at least 32 straight sections with 6.2 meter long or around 6 meter long to install the injection system, RF cavities, and most importantly for the advanced insertion devices. So this gives the overall present layout of the facility. We have 500 MeV Linac injector and 500 to 6 GeV booster synchrotron work as a injector to the 6 GeV electron storage ring. So more on this recent updates on the overall project overview by Dr. Mangesh will be on March 28 as well. So historically, we have designed one lattice, what we're calling now is a version 1 lattice, which is based on this 7-band Achromatic configuration, where we have used only the homogeneous field dipole and combined function dipoles. So as far as the emittance is concerned, we have already achieved 150 picometer rad. Okay, and based on this, we have prepared a preliminary design report in February 2022. So, however, this has some more requirements. That is, this lattice is very compact. This has a little space to install various engineering components. And the beta function at the starting or at the end of the cell is high. So, we want to decrease these beta functions to improve the brilliance from the insertion devices. And the dipole which we are using in the central 3 dipoles, the yellow one is using the high gradient in the dipole magnet, which is really very high and very challenging to achieve in the combined function magnet. And also we face the small dynamic aperture, which is necessary for this kinds of machine to have high value for this to achieve the high for off-axis injection. And most importantly, the sextupole strength which is really required to improve the dynamic aperture, are really, really huge. This is order of 5 kilotesla per meter square. So this lattice now is in the continuous optimization and iterations to accommodate the various engineering components. And there's a chance further to reduce the beam emittance better than 150 picometer rad. And we also add the one source of the synchrotron radiation from the bending magnet. The central dipole in the lattice, we will increase the magnetic field up to 0.65 Tesla or so. And these moderate beta functions to satisfy both the requirements of the injection as well as the brilliance from the insertion devices. And also, the most importantly, to satisfy the injection, we need high dynamic aperture and of course with the reduced extrapolar strengths. So with these changes, now we call this lattice as a lattice version 2. So this is the overall scenario of this present lattice, where we have 32 stress section, again 6.2 meter long. And minimum separation between the magnets we kept on 100 mm, because we are considering that presently we are considering on the electromagnets, we need a space for the magnet coils as well. And further requirement of the beam diagnostics, vacuum components, and the various other magnets like fast corrector and so on. So overall, we see the overall size of the ring has to increase. And ultimately, we are converging to the circumference of around 960 meter, considering the RF frequency of 499.75 and harmonic number of 1600. So with this, so we have accommodated most of the engineering components now, and now we have only the degrees of freedom to play with are the magnets and their strengths. So, so next, the choice is to really reduce the beam emittance further. As we know, the beam emittance is given by this very standard formula in electron storage ring. And this is proportional to the gamma square, which is nothing but the energy of the electron. And there are the three other parameters which are decided by the lattice design. And one is the known as the quantum excitation, and another radiation damping. And this is the two completed process in which we achieve the natural beam emittance. And third important parameter is the damping partition, and one can play with this damping partition to further reduce the beam emittance. So I will give you some glimpse on this and how these numbers are further reduced as compared to the homogeneous field dipole magnets. So our aim is to reduce this I5 and increase I2 and increase JX. So one innovative idea is to include the longitudinal gradient variation in the dipole field itself. If we see here, this is the homogeneous field, and this is the magnetic field variation along the length of the magnet, keeping the bending angle same. So this will help really reduce this I5 integral, which is nothing but the scale magnetic field normalized with the energy. So one can allow the maximum field at where the dispersion is low, so that this dispersion invariant achieves a lower value. So in that way, we can minimize the quantum excitation term and ultimately reduce the beam emittance. And this LGB profile not only reduce the beam emittance, is very, very helpful to generating the high dispersion in the zone where the sextopoles are installed, so that we can achieve the efficient chromaticity correction with the reduced sextopole strength. Okay, and another way, if to increase this damping partition coefficient, there's a conventional method which we have already using in Indus 1 facility here. So we include this very this strong negative gradient or the vertically focusing component in the positive band dipole magnet. So since we are using a very strong quadrupole component in the positive band, we call this magnet as a dipole quadrupole, not as the normal combined function magnet. So this helps in increasing this damping partition coefficient. So these medium 3 dipoles are considered as the DQ magnets, and these DQ magnets, the gradient is order of 37 Tesla per meter. It's really so huge, and this makes the lattice more compact and makes the J-axis more than 1. And as already pointed out, this dipole 4 has a magnetic field of 0.65 Tesla. And this is the source of synchrotron radiation from the bending magnet. This is in addition to the sources based on the insertion devices. And the next, another way if playing with this damping partition coefficient is the reverse of the combined function which we have standard in the third generation light sources. So we include differently that we have a focusing quadrupole, horizontally focusing quadrupole. We put small reverse banding so that this term h into eta become negative, and ultimately this negative sign become positive. Ultimately Gx is more than 1. So this is very important and very useful techniques to really reduce the beam emittance further. I mean, if we see the ring geometry, it looks like this positive band, negative band, and so on and so on. So there are the 4 quadrupoles focusing in nature, in which the very small reverse banding has been introduced. And this banding is introduced by just shifting the quadrupole by few millimeter. So these are not the very special magnets. These are just a focusing quadrupole, shifted by few millimeter. And the another advantage of including these anti-bands here is to have some degrees of freedom to control the beta function and dispersion independently. Otherwise, not possible, because the quadrupole here, placed here, if you change anything, if you want to tune the beta function, dispersion function will also change. And another important parameter is the increase the radiation damping, that is SR loss per ton. So this is inherently coming from the LGB profile, because we have this variation of the magnetic field along the beam direction. So we have high field and the low field. So this increase the radiation loss per ton, and also the reverse banding, which is the absolute bending angle is more than 360 degree. So this is automatically increasing the radiation loss per ton. So these are the multiple ways to really minimize this the beam emittance. And
Sir, 5
this,
more minutes.
okay, sir.
5 minutes.
Okay. So these are the parameter of the lattice which we have evolved as lattice version 2, where the beam emittance is now 103 picometer rad, and which we have started with the 150 picometer. And another important configuration of this lattice is the increase in the dispersion function at the sextopole location, where we can reduce the sextopole strength drastically. And this gives the overall positive bending angle, because we have to manage or compensate this reverse bending angle. The natural chromaticity is order of more than 100. And even with this, we have a sufficiently reduced sextopole strength. So this gives the beam quality at the insertion device and at the mid of the bending magnet 4, where the vertical beam size order of 6 microns. So this is a great challenge to stabilize this orbit within this level of numbers. And these are the types of quadrupoles, which is going up to 60 Tesla per meter, and there's high gradient quadrupoles around 80 Tesla per meter, and this is the dipole quadrupole of 37 Tesla per meter gradient with high field of 0.65 Tesla. And these are the anti-bands included in the 4 families of the quadrupole magnets. So during this linear lattice design, we have also take care of the nonlinearity effect. That is, we want to enhance the dynamic apertures. So most of the nonlinearity is cancelled by maintaining the minus sign transform between the sextopole pair here. So these 3 family of sextopoles are installed to take care of or correct the chromaticity and play with the amplitude dependent tune shifts as well as. And we are using the 2 octopole families. Normally there's one octopole family in ESRF and other machines. So we have included one more octopole here to take care of the nonlinearity coming from the sextopole to have the better nonlinear dynamics performance. So this compares the effect of including the 1 octopole and 2 octopole, where the amplitude dependent tune shifts are drastically reduced. And this shows the dynamic aperture necessary required for the off-axis injection is sufficiently high. And this gives the sextopole strengths, we keep this around 4 kilotesla per meter square. Initially it was 5,000 or 5 kilotesla per meter square. And this gives the number of magnets, the main magnets in the lattice. And now we continuously improving this lattice version 2 to lattice version 2.1, where the bending magnetic field is increased to 1 Tesla. And moderate beta function is now reduced to further lower beta values. So we having the high brilliance from the insertion devices. Once we come with this lower beta, we need a high beta injection cell to recover the beta this dynamic aperture, so that we can achieve the off-axis injection. So with these 3 configurations, so we are at the lattice version 2.1, where this beta function is already reduced from 11 meter to around 8 meter in the injection at the ID center. and the vertical beta function reduced from around 4 meter to 2.4. And here we have included the high field slice of the 1 Tesla to further enhance the SR characteristics from the dipole magnet. And this is the injection cell. This is required to really recover the dynamic aperture reduced due to this beta function here. And in order to maintain the periodicity of the lattice, we manage the phase advances in the low beta injection cell and the high beta injection cell to be same, so that this lattice become highly, you can say, pseudo periodic. And this shows the dynamic aperture with when we have a moderate beta function, lattice version 2, this is sufficiently high. And when we reduce the beta function, dynamic aperture reduced to around 12 millimeter. And finally, with this inclusion of this high injection cell, we already recovered the dynamic aperture required for the off-axis injection. So these are the just parameter comparison between the PDR lattice and the lattice which we have already under discussion and under machine advisory discussion. And we are already improved this lattice version from this to this, and we are in the better off in terms of the performance. And in summary, I will say that this is the design parameter which we have is 150 picometer rad. Now we already achieved close to 100 picometer rad, consisting of very advanced dipole profiles into the lattice. And we have increased the magnetic field from 0.6 to 1 Tesla to increase the SR characteristics from the dipole magnet. And already we have achieved sufficient dynamic aperture for off-axis injection. And these are the studies which are under progress. And I recommend the audience to please visit these following papers during the poster presentation, giving the various details on various aspects. So thank you very much for your kind attention.
Thank you, Riyasat, for a nice presentation and very timely you completed in time. Time for one quick question, if anybody please. Okay, if there is no question, maybe you can take up the question during the key session. So thanks once again.
Okay. Thank you, sir.
So we now move to oral poster presentations, and these will be presentations. So I invite, the first presentation is by Manya Yadav on beam optical design and optimization of second order 90-degree achromatic bend for electron beams. So we'll try to finish it in 4 minutes since we are running out of time. And we'll not have any question answer session here because we'll be presenting the work in the poster session. So the detailed question and answer can be done there. Check.
Okay. Can I start? Okay. Good afternoon, everyone. My name is Manya Yadav. I am BSc third year student from University of Delhi, and I'm currently exploring my research with the help of IUAC Delhi. And today here I'm presenting beam optical design and optimization of second order 90-degree achromatic bend for electron beams. So our main objective was to design a second order achromat 90-degree bending for 1 EV electron beam. We did so by optimizing the beam transport matrix to correct the chromatic and geometric aberrations. Chromatic and geometric aberrations are imperfections in the beam transport that occur due to the energy spread. We reduce the second order transfer matrix coefficients R16, R26, T166 and T266 to 0. Generally, we use sextuplets to correct second order distortions, but in our design, we achieved so without using sextuples. Before I proceed, I would like to briefly talk about what are achromats. Achromat in a beam optic is a specialized lattice design that helps minimize chromatic aberrations. They ensure that particles of different energies follow different trajectories but reconverge at the same point, reducing energy-dependent beam spread. The achromat that we designed successfully achieves this without using sextuple magnets, and it enhances the beam quality. We took the help of simulation tool COSI Infinity to achieve so. We used dipole and quadrupole magnets for second order corrections. We analyzed the beam optic parameters and minimized the matrix coefficients to maintain the beam focus. This helped us address the geometrical aberrations from magnetic field imperfections. So here we can see the optics plot of transfers in X plane and similarly in Y plane. Our key results and findings were achromaticity was maintained and beam quality was enhanced, reducing aberrations. We eliminated the need for sextuples, and the total length of our achromat was 6.9 meters. And these are the values of matrix coefficients that were achieved. Our design can be used in systems where high precision of beam is required, such as synchrotron radiations, medical accelerators, free electron lasers. And these are the references that I used. Thank you so much, everyone.
Youngest participant here.
Thank you, sir.
You can have question and answer in the question.
Okay, sir.
So now we move to the second talk by Atanu Datta, beam dynamical study of 50 MeV proton drive with cyclotron for annealing function. Hello.
Good afternoon, everybody. Good afternoon, everybody. So I will be presenting our recent work on beam dynamical study of the 50 MeV proton driver cyclotron for ONURI project. So ONURI project is basically associated with the production and acceleration of radioactive ion beam or rare ion beam. So in this project, we have designed a cyclotron 50 MeV 200 microampere proton cyclotron that will produce radioactive beam via nuclear reaction, and that radioactive beam then ionize and will be accelerated. So recently we have completed the magnet design, physics design, and it has been published in this paper. But in this paper, the beam dynamics we have presented that is different from whatever we are presenting here. So from the design magnet, first we have calculated the magnetic field in a plane, and from that magnetic field, first we have calculated the equilibrium orbit, static equilibrium orbit. That means these are the orbits where we assume along a orbit energies remain same. And from after identifying that static equilibrium orbit, from that orbit we have calculated this radial and vertical Betatron tunes. And this blue line for I is equal to 0 microampere, that we have calculated for static equilibrium orbit. Then we have estimated whether how much it has effect on space charge. So so for that we determined the tune depression from this relation, and we found that for 200 microampere, 500 microampere, they are very close to the zero value, and we found that at 500 microampere it is only 3.5% deviation is there. So for this present calculation, we have just ignored the space charge, though there is a effect we have indicated in our paper. but it is also required. Without space charge, calculations are also required. In the next hour calculation, we have calculated the coherent radial oscillation. Now, what is this coherent radial oscillation? It is the oscillation of the beam around the static orbit, static equilibrium orbit. So for that, what we have done, uh, after calculation of static equilibrium orbit, we calculated the accelerated equilibrium orbit. And what is that accelerated equilibrium orbit? It means that for a particular position, the deviation in r, means radial deviation in radial position and momentum, we denote it by x and px from static orbit, that deviation should be minimum. And that we have calculated in our simulation. We found that, okay, so for that, we have taken one central particle, means this is the accelerated equilibrium orbit, and around that 20 representative particles. Actually, these are not circles, these are actually ellipse. It looks circle here. And for all the particles, we calculated its xpx, and it comes out this like this. And if you see this property, this is the amplitude of radial oscillation, this AR, you find that this red dotted line, this is actually the central particle for accelerated equilibrium orbit, and these are the rest of the 20 particles radial oscillation around that. So it is actually, it indicates that it's not very high actually, it indicates that our design field is very good. Next we calculated,
in a minute. Yeah, in a minute.
time over? 1 minute, okay. So next we calculated the beam distribution on the stripper. Now in this cyclotron, stripper foil will be used to extract the beam. So what we have calculated, for two energies, suppose this is 50 MeV and this is the 30 MeV. In these two energy location, we calculated the beam distribution on the stripper foil. So this is the radius and this is the energy. You can see this 50 MeV beam, roughly corresponds around 5 mm from both this figure. Means if we take stripper 5 to 6 mm, then the energy spread will be less. If we take bigger stripper, then energy distribution will be more. So final conclusion is that space charge calculations at beam current of 200 microampere reveal a minimum impact on beta-ton tunes. Multi-ton extraction occurs at stripper position with only a slight energy spread. So thank you. Please complete. Okay.
Now, the next talk by Abhishek Padi.
So I'll be presenting on behalf of Abhishek. Yes. Yes. So so I'm presenting on behalf of Abhishek. He is not here, so that's why. So I'll be presenting the study of effect of spherical aberration due to solenoids on high intensity proton beam in MEPA1 LEBT. So MEPA1 LEBT transports 30 keV 10 milliampere proton beam from ECR ion source to the RFQ, and the aim is to match the beam parameter, and it consists match the beam parameters, transport and focus the beam. It consists of three solenoids and a bending magnet and drift sections. So in this LEBT, the role of solenoid is to focus and to change the twist parameter values so that it matches with the input twist parameter which is required at RFQ. And the issue while using this solenoid is of a spherical aberration. So it caused by inhomogeneity in this magnetic field across the aperture. So the magnetic field on the axial is, it varies as we go to different radius. So that's why this spherical aberration come into picture. So this leads to emittance growth and degrades the beam quality, which will be further amplified. So what is happening is particle at different radial position is experiencing varying focusing strength, and this causes the particles to focus at different points. This is what mean by spherical aberration, and this is leading to nonlinear focusing. So this induces emittance growth as explained earlier. And this spherical aberration is found to depend on several geometrical parameters like solenoid length, aperture, solenoid current, and these things he has studied. So there is, as we know that this LEBT is very important for high intensity beam. So we need to minimize these mechanism. And for this, understanding and reducing spherical aberration becomes very crucial. So he has done design in Poisson. So he has done a design for solenoid by varying its length, aperture, and outer diameter. So he, 4 solenoids he has studied of different aberration coefficients. So these solenoids are basically at different spherical aberration coefficients are achieved by changing the length. Aperture has been kept same for all. Though he has studied the dependence of this spherical aberration on the aperture also. And so this figure represents the cross-sectional view of soft iron yoke enveloping the current carrying coil of solenoid, and the beam line will be this side. So, and this figure here, it represents the axial component of the solenoid. So this is the axial component, and as the radius changes, we can see that this changes. Like we are taking at different radius, what is the BZ. So this is the reason for spherical aberration, and this is the field inhomogeneity which he has shown here. So the spherical aberration coefficient is defined as in terms of BZ, like BZ along R is equal to 0. So this is defined like this, and the focal length changes with these spherical coefficient in this manner. So this spherical aberration he has studied for different by varying length. So he has found that these two coefficients, what I have explained in the previous slide, they both decreases with increase in length. And this is because when we increase the length of the solenoid, the field is becoming flatter. And similarly, for increase in aperture, he has found that these coefficients decreases. And with increase in this spherical aberration, the emittance increases. So it is very crucial to decrease this spherical aberration coefficient. So he has studied for 4 different solenoids. He has transported this 10 milliampere 30 kV proton through this MEHPA LEBT for 4 different types of solenoids. And these are the coefficients, spherical aberration coefficients, and these are the emittance values. So for solenoid 4, the emittance improves, which is of longer length. Thank you, and special thank you to RRCAT colleague, which like the slides actually changed at last minute, so we could not mention here, but special thanks to Gautam Sinha sir and others. Thank you. Thank you so much.
The next talk by Manas Ranjan Mishra, Design and Optimization Studies for MEHPA-1.
Yeah, give it. Okay, I will be presenting this design and optimization studies for MEHPA-1 RFQ that we have done. So this is the plan of talk. So I will start with an introduction, basic introduction. Basically, I will specify the design specification requirements of MEHPA-1 RFQ. Then I will move to beam dynamics and cavity dynamics, and finally conclude. So this is basically the MEHPA-1 layout. So Dr. Rajesh Kumar has already told about this MEHPA-1. So RFQ is the first accelerating structure which will accelerate 30 keV beam to 3 MeV in the normal conducting section. So the table here that represents, the table here represents the requirement specification of MEHPA-1 RFQ. Specifically, I want to emphasize the differences between the LEHIPA RFQ, which is successfully operating at LEHIPA facility in BIRC. So the basic specification difference is highlighted in green color. So that is the injection energy. In injection energy, we have reduced to 30 kV, and the frequency is 325 megahertz. So this frequency 325 megahertz is decided by the SSR1 frequency. So that is 325, and this 30 kV is basically from our operational experience of the ECR ion sources that we have at our experimental facility. So what we have observed that the
emittance is better around that 30 keV. So that's why we have taken 30 keV as the injection energy. But again, we have to, so the requirement is that we have to keep the length of the RFQ within 4 meter, and we cannot increase the modulations to a very high value because that may lead to surface electric field going beyond the Kilpatrick limit. And similarly, the synchronous phase, we cannot vary it abruptly because that would lead to basically longitudinal emittance blowing up. So basically we have to vary all these parameters it has to be varied very precisely so that we meet all the stringent requirement specification, but at the same time we have to minimize the beam loss, energy spread, emittance growth, etc. So what we have adapted the conventional RFQ design approach proposed by LNL. So we have, like RFQ is divided into 4 segments, we all know. So, and for parameter generation program, we have basically developed one in-house parameter generation program, and the output of this program is fed to, basically it goes to Lattice for iterative beam dynamic studies. So that is the most important, and this is the beam dynamics results. As you can see, the variation of modulation and synchronous phase and the RMS emittance, and the basically this is the input distribution and this is the output distribution at the end of the RFQ. So as you see, the transmission is around around 99.94%. Similarly, and this table basically gives the beam dynamics results. And this particular plot shows basically the placement of, so basically this RFQ is a 4 meter length. So for so it is divided into 2 segments of 2 meter each, and it is joined by the coupling cell. So the coupling cell basically makes the RFQ insensitive to higher order mode perturbation, higher order TE21N mode perturbations. So the placement of this gap, where basically we separate the 4 meter RFQ into 2 different segments, as well as for mechanical fabrication wise also this 2 meter is again divided into 1 meter sections. So the placement of the gap and the width of the gap, that plays a very important role. So as you can see in the first plot, this plot, so basically in LEHIPA what we have done, we have placed the gap where the Ez is 0.
To wind up.
Okay. Ez is 0, but here that we have changed and we have made that location of the gap at a point where the synchronous phi s is 90. So that leads to this envelope, beam envelope similar to the RFQ without any gap. So that's why then we have done systematic 2D optimization studies to basically optimize the transverse geometry. So here our aim is to basically get the frequency TE210 frequency at 325 megahertz. However, to minimize the RF losses and to keep the Emax within Kilpatrick limit, and at the same time, so we have to look at the dimensional and fabricational feasibility. So these are the results which I can show you that during the poster session. Similarly, we have done comparison studies between 2D and 3D results because we have many asymmetric structures. So to basically optimize those asymmetric structures and to see the effect of those asymmetric structures, we have done detailed 3D optimization studies. So this is basically the convergence of, we have done also the convergence studies.
The conclusion and detail.
Yeah. So this is basically tuner and then beginning cell, end cells, and the coupling cell designs. And finally, we have done these dipole stabilizer rods. So we have designed that so that the unwanted dipolar modes, they can be far off from the quadrupolar mode. So the conclusion is we have designed the MEHIPA-1 meticulously to achieve the high transmission efficiency, stable beam dynamics, and optical electromagnetic performance. And final design is successfully balances the beam quality and power efficiency. And finally, we will be going for fabrication and RF high power testing once we go through the project. Yeah, thank you. Yeah. Sure, sorry.
Transport of laser plasma accelerated.
साइन जी
ये देखिए ये यहाँ ये पॉइंटर आके
ये वाला
एरो
So good afternoon, everyone. I'll be presenting our work today on focusing in transport of laser plasma accelerated proton beam using high field pulse solenoids. So let us first begin with the acceleration scheme. So here, when an ultra-short intense laser pulse interacts with a thin foil target, it leads to generation of plasma on the target front surface. Now, when the laser pulse interacts with this plasma, it leads to generation of highly energetic electrons having energy hundreds of keV to few tens of MeV. These energetic electrons then propagate through this thin foil target and escape out from the target rear surface. Leading to formation of an electrostatic sheath field. This sheath field is typically of the order of 10 to the power 12 volt per meter, which is quite high. So this field ionizes the hydrogen contaminants present on the rear surface along the target normal direction, owing to which this mechanism is called target normal sheath acceleration or the TNSA mechanism. So directly coming to our experimental investigation, we firstly accelerated the proton beam and characterized our proton source. Here is our experimental schematic. We focused the laser pulse using a 45-degree off-axis parabolic mirror onto the thin foil target, which are typically copper targets. The proton emissions were characterized using a Thomson parabola ion spectrometer, radiochromic film, and the proton charge was measured using current transformers. So here is the beam profile of the proton obtained on different RCF layers at a distance of about 3.5 centimeter from the proton source. This is our recorded Thomson parabola ion spectrometer signal showing different ionic species that are coming out simultaneously in this system. From this TPIS image, we derived the proton energy spectrum. You can see that the maximum proton energy that we obtain here is about 6 MeV for this particular case. We also measured the proton beam charge. Here's the snapshot of the oscilloscope showing current transformer signal. So all in all, in this in a single proton bunch, we obtained a proton charge of about 80 nanocoulombs. Integrated proton charge of 80 nanocoulomb. So the same setup was then modified for the proton beam transport system. TNSA beam mainly are limited by two factors. One is the broadband energy spectrum, and the other one is high divergence that the proton source has. So to address this, we external focusing devices are used. We used solenoid based system for this purpose. So our the transport line that we are using was set up at our 1 petawatt titanium sapphire laser system. The same setup was now modified for this. The first solenoid was placed inside the vacuum system at a distance of about 6.5 centimeter from the source. This solenoid basically captures the proton beam and collimates it onto the mouth of the second solenoid, which was placed in air at distance of about 100 centimeter from the source. These two solenoids in combination focus the proton beam onto the focus point at a distance of 1.7 meter from the source, where a plastic scintillator was kept which recorded the proton beam profile in combination with a CCD camera. So now, before using the solenoids into the experiment, we characterize its magnetic field, and here this figure shows the current pulse and the generated magnetic field. One important thing in this process was to synchronize the solenoid with the laser arrival timing, so that the proton bunch encounters the peak magnetic field when it passes through it. Now, these are our results. So the proton beam was successfully focused and transported to a distance of 1.7 meter. The focused beam size was about 2 mm in FWHM. And here are the results for 2 MeV, 3 MeV, 4 MeV, and 5 MeV beam. We selected the desired focused proton energy by adjusting the magnetic fields of the two solenoid. So all in all, we successfully developed and demonstrated a transport system for laser accelerated proton beam of energy 2 to 5 MeV to a distance of about 1.7 meter from the source. And these focused proton beam we are currently using for biological cell irradiation experiments. Thank you.
Thank you so much.
ये ड्रॉप डाउन है
Okay.
ये पॉइंट है I am Samir Ranjan Sahu from BRC Mumbai, and my talk is that simulation and design of beam chopper for this medium energy and high intensity proton Linac. So these are some key points of my talk. The first is the some basic principle of the electrostatic chopper, and then I will talk about some of the simulation that I update, and next I will be talk about that we get from this simulation and all, and last is the now what we get in the lab experiments. So now let's move to the first slide. So it is on a basic principle of electrostatic chopper. That is, the electrostatic chopper is just a deflecting capacitor. That means it has some two plates, and that was applied some potential. Due to that, the beam starts to bend. So in order to give that is a clear platter beam. So we have to put this beam chopper for a that is a short period of time. So now that we know now when that B is perpendicular to E, then the path of the charge particle will be parabolic in nature. Suppose in this case that is the length of the capacitor, and D is the gap between them. That is the Q is the charge, and M is the mass of the charge particle. So from this we can get that in order to not to hit this plate the charge particle, it is the dependence on L and D, so that the charge particle will not hit this capacitor plate, and it will hit to the somewhere else in the beam line. So that as this medium energy high intensity is a CW compatible proton Linac, so now we have to put some beam dump over there to minimize this local effect and all. So it is the deflecting angle, that is theta is equal to tan inverse of QEL divided by M into VZ square. That means Q into delta V, that is the potential difference between these two plates, and D is the gap between them that I talk about. Now for a given energy of the beam, the deflection angle is given by theta is equal to tan inverse of Vp L divided by 2d Va, where Vp is the plate potential and Va is the that is the accelerating potential from which this charge particle is being accelerated. Let's move to the next slide. It is the chopper plates that I have talking about. These are the chopper type is the electrostatic, and the particle energy is for the 30 keV, and the beam current is 10 milliampere. All these simulation has done for this beam parameters. So it is the length is about 74 mm, and the gap is about 80 mm, and the electrode voltage that I am talking about is plus minus 2.5 kV. That means it will give the net potential difference of that is 5 kV. So it is the actual lab view. So now we have this gas line. We have putting this gas over here, and it is the plasma chamber. So it is the place where we have to put this electrogeometry. So next is the CST simulation. It is showing this is the beam
Wind up in 1 minute.
Okay, so it is showing this the beam bending due to these two places, and it is the 2D field map that is giving this beam bending, and it is the deflecting angle that I am talking about. So now we get 4.4 degrees from this theta calculation, and from this CST calculation we get about 4.1 degree, and this simulation we are getting from 5.2 degrees. So next, it is the DSO interface that I am talking about. It is that is the trigger pulse. It is the beam pulse, and it is a chopper HP pulse, and it is a chopped beam pulse. So now for this now we are talking about this beam pulse having this 5 millisecond pulse width, and it is done for this beam energy of 30 keV. And the beam current was 8.1 milliampere or something, and the chopper HP about 5 kV, and it is applied for about 250 millisecond. So it is showing that is the rise time of this chopped beam pulse, and that is the chopper pulse, and we are getting about 9.1 millisecond, and the chopper beam pulse is about 11 millisecond. So now I have taken this geometry in order to minimize the capacitance, so that we can get the less rise time and fall time that will improve the beam quality. So all over this. So now thank you so much. Thank you.
Thank you. Designed to improve dynamic virtual injection scheme in industry storage ring lattice.
Hi सूरज जी, listen. बढ़िया से. Arrow up down और ये बीच में पॉइंट.
Good afternoon, everybody. I am Suraj Prakash and will be presenting my paper on the topic injection cell design to improve dynamic aperture and to facilitate injection schemes in industry storage lattice. So already a detailed discussion is presented by the Dr. Yasir Hussain on the industry lattice. So this is the lattice. This is one super period and distribution of magnets and lattice function. So these are the parameters of industry lattice. The circumference is around 960 meters and the natural limitance is around 103.4 picometer head. The model beta function are decided here to facilitate both injection schemes as well as insertion devices, but the requirements is there. So we are optimizing these lattice further to satisfy additional requirement. Like first we need low beta at long state section to enhance the photon beam brilliance, and second is the inclusion of a super band at the center of each super period to tap the synchrotron radiation source. So already we have included a dipole quadrupole type magnet, but this may present problems while commissioning. So we are switching to superband system. So further, the low beta configuration will itself present further challenges because it will demand very high sextupole strength and the dynamic aperture will get lower for the off-axis injection, and the kicker strength when we are using initially 4 kicker injection scheme to inject the beam. So to mitigate these issues, we require very high beta injection cell with a clear space of 7 to 8 meter to for the injection systems, including kickers and septums. So first, we need to design a low beta lattice at the long state section and inclusion of superband. So the BM4 magnet is replaced by this system. Here is the dipole, which has a 1 Tesla field, and these are the DQ magnets. But this system increases the circumference by 6.4 meter, and fortunately, it is foreseen that the transverse gate walls included in the lattice are no longer required. So this saves around 9.6 meter. So for a fixed circumference, we are left with the 3.2 meter, which is utilized to create the long state sensor for the injection system, which is around which will be around 7 to 8 meter. So this is the lattice configuration with the low beta. Here we can see that from 11.3 meter to we are achieving here 8.35 meter. So these are the further optimized LGB profiles, and these are the dynamic aperture. As we can see that.
One more minute.
Sure, sir. This dynamic aperture get reduced, so we need to optimize this lattice further. So for this, we designed an injection cell. So we followed two approaches. In the first approach, we replaced the doublet with the triplet, and the second approach, the dipole is breaked into two parts, and quadrupole is included here. So our motive is to match the parameter here with the at the initial condition at this dispersion bump location, and these are our requirement. Sorry. So with this, these are the results in approach 1 as well as in approach 2. We are achieving more than 15 meters and clear space of around 8.1 meter in the approach 1, and approach 2 it is around 7 meter. So we can see that dynamic aperture significantly improved with inclusion of a high beta cell. Here we can see that with the RF on and RF off. These are the list of parameters. So we are not very far away from the designed one. We are at the 109 picometer rate, but at the cost of this increased SR loss. So with this, also the beta function reduces here. So with this, I conclude my presentation.
Thank you, Suraj.
Okay. So good afternoon to all. Actually, this is a piece of theoretical work in which in a very simple way, a formulation for the SR loss per turn is derived up to second order in the momentum offset. And there is an interesting discrepancy with the simulation tools. So I'm going to present that. So in electron storaging, the loss per turn from any electron is actually given by this formulation. This D is the dispersion and rho is the bending radius, and delta P by P shows the fractional momentum offset of the particle. And this shows a path of the electron followed by in a ring, and this is the radiation emitted, power radiated by the electron. So this actually formulation depends on two factors. One, electron's energy, and the other one is what is the path followed by that electron. So if we, actually in literature generally, this is the starting point for deriving this formula. However, if we want to derive this formula up to second order, we have to convert this expression also up to second order, and then this radiated power has to be calculated up to second order in the momentum offset. If we do that, this is just the path length followed by the electron up to second order in the momentum offset, and this is the power radiated by the electron. Here gamma is the electron's energy and R is the bending radius of that particle. And if we convert in the magnetic field, then it shows like this E square by E square term. And if we convert this again up to second order in momentum offset, the finally power radiated by the electron up to second order in momentum offset will be look like this. If we combine the path length and this power in the integration, we find finally the radiated energy per turn by the electron in this fashion. So this is the momentum independent term. This is a momentum offset independent term. This is the first term which is depending on the first order of the momentum offset. This is term which is showing the second order momentum offset. In general, if we want to calculate the damping time in electron storage ring, up to this point, formulations are used. This is the new added term here. Now, to calculate this term, for an example, I used two lattices, INDUS1 and INDUS2. Why I have chosen these two lattices? The reason is very clear. INDUS1 is a very small ring, means bending radius is very less, and it has a gradient in the dipole magnet. You can see here, this K shows the gradient in the dipole magnet. So this radiation depends on the gradient in the dipole magnet, and INDUS2 is a different kind of lattice in which there is no gradient in the dipole magnet, and it is a larger ring, means a larger bending of radius. Now if we compare,
One more minute.
yes,
One more minute.
if we compare the results using simulation tool, elegant, there is really interesting discrepancy. This curve shows the formulation which I have derived, and this shows the radiated energy with momentum offset using elegant. Elegant is giving lesser nonlinear effect than the obtained formulation. Still, elegant uses up to third order terms. So this is really interesting to show. This is only due to second order effect. There is no significant third order effect which can bring this nonlinearity to this nonlinearity. Because you can see here symmetric effect due to elegant, means there is no signature of the third order nonlinearity. This is up to second order, and second order nonlinearity is lesser than the analytical formulation. This can also lead to a change in damping time up to 10%. That is large enough. And in case of INDUS2, which is a very large ring without gradient in the bending magnet, elegant and analytical formula matches well. So this is my conclusion. The simulation tool and analytical formula differs with each other. And in case of damping time, which I have not shown here, actually in case of INDUS1, this differs up to 10%. This is a large number. And due to this difference in the code and analytical result, definitely more rigorous analysis is required. Whether the code is giving correctly or analytical formula has to be modified or model has to be modified. This has to be checked thoroughly. As far as I believe that formulation is correct. And due to change in equation of synchrotron motion, damping time may be different. So these are the references, and thank you.
Thank you, Amlendu.
सब ये पैरेलल में लगे हुए हैं।
इसको रख दो यहीं पे।
अब नीचे नहीं गिरे, देखना ये पॉइंटर है, एरो अप डाउन।
Good afternoon. Today I'll be presenting the physics design of the pre-injector for the proposed industry. The pre-injector for the proposed industry, as per the present requirement of booster of industry, is a 500 MeV electron Linac of S-band. So this was presented in detail by Dr. Vineet sir in the morning session today. So it needs to be operated in different modes. So that are high brightness mode and high resolution modes. And these modes are different in respect of the total charge, number of bunches, bunch spacing in the macro bunch. And however, if we see the energy spread and the RMS emittance, this is a requirement is similar for all the modes. Hence, this high resolution mode C, which has the maximum charge per bunch, that is 1 nanocoulomb per bunch. So it was more stringent to obtain. So this is the present layout of the 500 MeV pre-injector Linac, which is currently adopted. So it will have a 90 kV gun, and it will give beam current ranging from 40 milliamperes to 2 amperes as per the mode requirement. And this 1 nanosecond beam from the gun, it will be bunched to around 50 picosecond in the subharmonic pre-buncher. And then we'll have a traveling wave buncher section where this 90 kV beam will be actuated to 15 MeV, and it will be further bunched to around 6 picosecond. And then we'll have a traveling wave constant gradient accelerating section, and it has 10 similar structures, and it will be of 2998.5 megahertz, 2 pi by 3 mode, and disk loaded structure. And finally, we'll be getting the energy of 500 MeV in 10 sections. And after the structure, we'll have energy filtering system. This is required because it will scrap the off energy electrons so that we can get the required energy spread in all the modes. So a little detail about all the sections. So this is the cross-sectional view of the pre-buncher cavity. This cavity will give a 20 kV voltage modulation to the 90 kV beam. And after this, we'll have a drift space which has been optimized such that we have the minimum RMS bunch length at the input of the buncher section. And these are the geometrical parameters. Then after this, we have the buncher section. Buncher section, as discussed, it will further bunch the 1 nanosecond beam to around 50 picosecond, and this structure is of disk loaded type. This is a cross-sectional view of a disk loaded constant impedance structure, and these are the single cells and a half cell. And will be an integrated structure, means we'll have in the same structure, we will have 8 bunches cells, and then we'll have 60 extracting cells. Total length is around 2.2 meters, and the input RF power requirement for the peak is 6 megawatt. And these are the optimized geometrical parameters. Then we have the traveling wave section. So we'll have 10 identical sections, and each section will have around 114 cells, and the total length of one section is 3.8 meters, and the input peak RF power requirement is 21 megavolt per section. And since there is a constant gradient structure, so here the aperture radius of each cell is suitably optimized so that we can get constant electric field in the absence of beam. And here this aperture radius variation and the cavity radius variation is shown. And there is one schematic of the transport line between the accelerating sections. And these are few results for the end-to-end beam dynamics that we have performed for the complete 500 MeV structure. There is a longitudinal electric field for all the sections. Phases were suitably optimized to get so that the bunch is placed at the correct phase for maximum acceleration and the minimum energy spread. Then there is the optimized magnetic field profile. And this is most stringent in the lower energy part where the space charge effect is significant, and we can control the beam focusing and the emittance growth. This plot shows the beam focusing, bunching in the pre-buncher and the successive drift, and this is the beam evolution plot for the high brightness mode. And finally, these are the results for the high brightness mode, which was the comparatively easiest mode for us, and high resolution mode, which was most stringent due to the maximum charge per bunch. And this plot shows this in this table we have listed the beam parameters after Linac and after the energy filtering system, and we were getting the required parameters and both the modes. So these were the two extreme modes, and here we were getting emittance and the energy spread for both. Thank you. Thank you.
PPT वाला एक नीचे वाला
Good afternoon to all. I will be discussing lattice design studies for the proton and carbon therapy synchrotron. While traveling in the body, and they give maximum dose at the location of Bragg peak, which is made to coincide at the to the tumor location, and no dose after it. So more effective and selective killing of the cancer cell is done compared to photon. In carbon therapy, carbons have even narrower Bragg peak, so they give more ionization density at tumor location. Also, being a heavy particle, so while traveling in the body, it have lesser lateral scattering, so it gives additional advantage over photon therapy. So due to these advantages, we are designing a carbon and proton synchrotron for therapy purposes. These are the various facilities around the world. Actually, 14 carbon facilities are currently operating in the world, and they are also using carbon proton therapy also. So design criteria. First, our lattice must be compact as it has to be built in the hospital. Yet it must provide sufficient uninterrupted drift space for different subsystems. Also, there will be slow extraction in the synchrotron, and for that RF knockout scheme has been selected. For this, our machine should be operating near 1/3 integer in horizontal plane. The sextopole which drive the resonance must be placed at non-dispersive region so that it affects the chromaticity less, and their Metatron functions should be well separated in horizontal and vertical plane. Magnetic septum is also placed in non-dispersive region where beta x is high. Also, the herd condition must be fulfilled. This DN normalized dispersion and its derivative is related to the chromaticity and normalized sextopole strength. When this condition is fulfilled, the kick from the electrostatic septum becomes momentum independent. So the all the different momentum particle get this
and find it out.
reach the septum location, and no loss extraction is possible, low loss extraction. So based on these criteria,
Shall I continue? I can roughly.
Pradeep, one more minute.
slide आ गया।
आ गया? Sorry.
नहीं और भी है।
I was just talking about how these three are related and whole accuracy depend on how we manage this thing. So we measure actually the
इससे पहला था, हाँ, yes, हाँ. So based on these criteria, we have designed a compact lattice whose length is 56.4 meter. All the other lattices in the world is around 60 to 61 meter. So this lattice satisfy all the criteria. This is the schematic of the lattice where resonance sextopole, electrostatic septum and magnetic septum are shown, and the location of that these components are such that it satisfies the Hertz condition. The maximum extraction energy is 250 MeV for proton and 430 MeV per unit for carbon. We will be operating at 2.7 and 2.1 tune. The Hertz
Pradeep, conclude.
From the Hertz condition, we can have this required sextopole strength, and maximum stable oscillation amplitude varies inversely with this strength. This is the graph showing the with the change of chromaticity how the sextopole strength and stable amplitude are changing following the Hertz condition. The tuning range, as we have to fix the nu x, nu y can be varied from 0.207 to 0.15, so it's a reasonable tuning range. Amplitude particles are reaching the third order resonance. So I conclude that we have designed a compact lattice in which sufficient space is available for different subsystems. Locations of resonant sextopole and electrostatic as well as magnetic septum are well optimized, and they make the lattice suitable for RFKO slow extraction. Maximum field gradient of some quadrupole is having some higher values, and we have to bring them down. Further studies on slow extraction are being done, and studies for injection scheme will be initiated. Thank you.
Thank you, Pradeep.
इस स्लाइड के ले क्या आगे?
हाँ,
और ये पॉइंटर, ये वाला. Okay, yes. Good afternoon, all of you. My topic is presentation topic of optimization and beam dynamics studies for ADS target facility at VCC Kolkata. So there are some activities ADS target related going on in BRC. So ADS target mock-up experiment facility has been set up in BRC to study the thermal performance of window and hydrodynamics of liquid metal, and if there is some design upgradation based operational experience in non-Newtonic environment. And in BCC we have 30 MeV 350 microampere proton beam. So this will create almost 10 to the power 12 newtons when it will interact with the lead bismuth. And third is
there is a critical challenge in ADS system to minimizing the beam losses during beam transport. So it will help us to reduce the activity in our target. So this is our mock-up loop experiment in BRC, where we have almost achieved 25 kg per second flow rate by injecting 100 SLPM nitrogen gas. And this is our medical cyclotron facility in Kolkata. Here we have ADS beam line 1.2. And this is our beam line. First you can see there is fast gate valve, then steering magnet, then collimator, then this is the first pair of quadrupole magnet, then there is Faraday cup, then there is bending magnet, and then that is our this is vertical section, and that is horizontal section, which is almost 9 meter in height. So when we transport the beam in our horizontal section, and this is your Faraday cup, we can see how much transmission is happening from a cyclotron to this place. So we have got almost 97% transmission. But when we further transport up to here to bottom of this vertical section, so we got only transmission 50%. So to minimize the beam losses, we have carried out the beam dynamic simulation in Tracebeam software. So this is a 1 sigma plot in X and Y. So you can see in 1 sigma there is no losses. But when we see this 3 sigma plot, so our beam vacuum aperture size is 100 mm. So in X you can see there is no beam losses, but in Y there is beam envelope is going above 50. It is touching to 60, and also in minus it is touching to 60. So there are significant losses near first pair of quadrupole, bending magnet, and second quadrupole, this quadrupole, because it is hitting the our vacuum aperture. So, but we have able to minimize our losses. So we got 90% transmission, and you can see this is the loss percentage curve. And how we optimize it? We have just reduced the strength of first pair of quadrupole. So you can see as we reduce the quadrupole strength, we got the transmission. What's happening, man? So as we reduce this quadrupole strength, we got transmission increases, and we got an optimal position where transmission maximum happens. And if you further reduce the strength of the quadrupole magnet, it will again reduce. So you can see this loss percentage here, where minus 4.1 and minus 3.8. So this is the loss percentage we have minimized, and you see that this is the beam sizes at the end of the target position we have got. So we have reduced our this beam envelope size. So numerical simulation has been carried out to estimate the beam spot and transport losses in L-band proton beam line for ADS experiments. So it has been observed that the beam waste before the bending magnet is strongly influencing the final beam spot and losses in the entire transport line. So the optimized parameters are obtained by varying the first set of quadrupole without changing any lattice element's position. Thank you.
Thank you.
ये तो पता है
नहीं बता दीजिए
ये एंटर है ये रोक दो
ठीक So good afternoon everyone. Myself Divyansh Pandey, and today I'll be presenting my work which is titled preliminary design of energy filtering system for 500 MeV pre-injector Linac for industry. So Indus 3, as has been mentioned in the previous talks, will be a 6 GeV storage ring synchrotron light source, which is envisaged at RRCAT. It will have a 500 MeV pre-injector Linac, followed by a booster and then a storage ring. It will be, for satisfying the booster requirements, it needs to be operated in two different modes of operation. One is high brightness mode and another is high resolution mode. For both modes of operation, the RMS energy spread is required to be less than 0.5%. So in order to achieve this, we have designed an energy filtering system that will only allow particles that are having 0.5% RMS energy spread. So the design of the system we have evolved is based on two bending magnet and one quadrupole. The optics we have designed is in such a way that it is an achromatic optics. That means that if there is no dispersion at the beginning, there is no dispersion at the exit. So these are my optimization criteria, like bending radius is kept sufficiently large so that we have a feasible magnet design. Same goes with the different parameters. For example, quadrupole gradient, we have restricted to 6 Tesla per meter. Drift length we have obtained as per the achromatic condition that we have worked out. I would like to mention here that there is an additional important parameter for the design of any energy filtering system, which is its energy resolution. So it has been taken care that energy resolution be very high, which should be less than 0.1%. These are my optimized parameters of energy filtering system based on these optimization criteria. And these are the plots. This shows the dispersion versus the distance along the reference trajectory. And we see that if there is no dispersion at the beginning, there is no dispersion at the exit. So it is an achromatic system. Same goes with the derivative of dispersion. Now this is a variation of energy resolution within the system, and we see that this particular location is having the minimum energy resolution. Means we can distinguish between two different energies best here for this optics. So this helps in deciding a location for scraper. Scraper is basically like a slit. So that will allow only 0.5% particles to pass through that are having 0.5% RMS energy spread. These are my quadrupole magnet parameters, these are bending magnet parameters. Now, as I mentioned before, that it needs to be operated in two different modes. So first is high brightness mode, and for high brightness mode, we can see that initially after Linac, we had 1.2% RMS energy spread, which after energy filtering system becomes 0.5%. Achieving the desired criteria, and same goes with high resolution mode. We had initially 4%, and finally we are also achieving 0.5% RMS energy spread. Thank you.
Thank you, Divyang. Once again, thank all the speakers and especially the audience sitting here for their patience. Thank you so much.
With this presentation, we come to the end of this session. We thank Dr. Vinit Kumar for conducting the session. May I request Dr. Arup Bandyopadhyay ji to present a memento to our session chair, Dr. Vinit Kumar ji. Thank you, sir. Now this session is over. All are requested to join for the tea and for the poster session. Those participants who have poster session today, they are requested to put their posters on the designated boards. Poster session is in the way. Okay, thank you. शाम को होगा ना, अभी कोई है भी नहीं सुनने वाला। क्यों अभी यहाँ पे दोबारा टाटा की नहीं है? शाम को होगा।